So, in the previous lectures, we've been talking about compounds. We have two different types. We have ionic compounds and we have covalent compounds. We've talked about their different properties. We've looked at the naming of the different types of compounds. And in the previous chapter or lecture, we talked about how to calculate molar mass of these compounds. So, now let's take a microscopic look at compounds. How are the atoms put together? How are those bonds made? What kind of bonding atom arrangement is there to produce these different compounds? So that brings us on to Lewis structures and bond polarity. So one of the really important skills from the previous chapters is you need to have a really firm understanding of electron dot symbols and how to count valence electrons on different atoms. Those skills are going to be really important when we're essentially putting together electron dot symbols and creating Lewis structures. So remember what an electron dot symbol shows. It tells us the number of valence electrons of each atom. So you need to know how can you look at an atom and predict how many valence electrons there are. And it's all on the periodic table. And remember that these electrons that you put around the valence shell of an atom, they're arranged into s and p orbitals around the element. And so those orbitals are where the valence electrons lie, and those are the electrons that are involved in bonding. So when we form molecules, we essentially mix different atomic orbitals of different atoms. So the s and p orbitals can come together of different atoms and create bonds. And once we take an atom and make a molecule, we essentially get these new types of orbitals. We go from atomic orbitals, when looking at just electrons around an atom, to these new sets of orbitals, or we can call them molecular orbitals, when we make molecules. And those orbitals are describing where the electrons lie when forming bonds, when atoms come together and form bonds to make molecules. All right. So again, we're taking a microscopic look at how atoms are arranging themselves to form molecules. So there are different types of structures that we can depict, or you can think of models. There are different models that we have to depict how molecules are formed. So we have this simple picture, or you can think of a model to describe the bonding involved in a molecule. So you can either use just, electron dot structures and start to put those atoms together, all right, and put them near one another. So that's kind of what you see here. Or you can make a Lewis structure, or what we call line structures. So instead of making all of these dots, every two electrons makes a straight line bond. So lines, these line structures, those lines indicate the formation of bonds, where we take atoms, put them together to form molecules. They come together by forming a bond. So these two pictures show the different structures of rubbing alcohol, or isopropanol, where this left figure, this is our electron dot structure. And the right one, this is our Lewis structure, where instead of electrons, every two electrons is replaced by a single line bond instead. So Lewis structure or line structure. Because no one wants to sit here and draw a bunch of dots. So we're going to represent our bonds with lines instead. So on to the rules for drawing Lewis structures. So we're mainly going to focus on the Lewis structures, where we're using lines to denote bonds. So these are the rules, the systematic rules we follow to make Lewis structures. I'll also note that these drawing rules will typically be for covalent compounds. So we're drawing covalent bonds, typically, but I'll show you a little exception later. But yeah, these rules are for covalent compounds. So the first thing that you need is a chemical formula. So typically a question will say, okay, draw the Lewis structure for this, this covalent compound where I give you the chemical formula. So that's the first thing you need in order to draw a Lewis structure, the formula. So once you have that chemical formula, first you need to count all of the valence electrons from all of the atoms. And you want to take the sum of all of those valence electrons from all of the atoms that are listed in the chemical formula. Take note of the subscripts that are there. All right. Then once you have the total number of valence electrons, you want to write the chemical symbols in the order in which they're bonded. All right. And so the way we bring atoms together, typically the first atom that's in the chemical formula is the central atom, except when it's hydrogen. So keep that in mind, and that will tell you how the compound comes together. So if I have a compound like CH4, right, that's a covalent compound, I'm going to put carbon in the center, and then I'm going to put hydrogen, those other 4 hydrogens all around it. So that's what I mean by write chemical symbols, how they're bonded. And then the second part, place one covalent bond between each of the atoms. So now we want to, put all those atoms together to form one molecule. So for this example, CH4, I would put a line or a covalent bond between all of those atoms, connecting the outer atoms to the central atom. All right. So yeah, remember this tip here is that the first atom written in the chemical formula is usually the central atom. All right. So remember, each of these bonds that I drew, each of these lines, requires 2 electrons to form a bond. So on to step 3, if there are any extra electrons that you haven't drawn yet, while keeping in mind what is the total number of valence electrons from that first step, you need to start adding lone pairs to the outer atoms first to fulfill their octet if there's any extra electrons. Then, if there are still extra electrons, keeping in mind that total valence electron sum from step 1, then you want to start putting those extra electron pairs on the central atom. All right, so fill the extra electrons on the outer atoms, then the central atoms, until you have drawn an equal number of valence electrons in the entire structure. So once you've drawn all of the electrons, the valence electrons, from step 1, you need to check the octet rule on all the atoms. All right, and then I'll talk about this last step in a later slide. But remember that whenever you draw a bond or a line, a covalent bond or a line, that equals 2 electrons. And then whenever you draw a lone pair, that also equals 2 electrons. So each time you're making a bond, you use up 2 electrons from your valence electron sum from that first step. So I think it's best to just do this in practice. So we'll do a lot of practice here. So let's do some examples here. NH3, of the Lewis structure for NH3. So I'm going to follow the steps. So we have our chemical formula here. All right. So our first step is to count valence electrons. All right. So I'm going to add all those up. So nitrogen, if you look at the periodic table, nitrogen is group 5A. So it has 5 valence electrons. And then there's hydrogen. Well, there's 3 hydrogens. All right, because of the subscript 3 there. Hydrogen, it's in group 1A. It has 1 valence electron, but there's 3 of them. The other way, 3 times 1. So all of the atoms, I'm counting up their valence electrons. So nitrogen and 3 hydrogens, there's a total of 8 valence electrons. So I have to draw 8 electrons in the structure. So that's step 1. Step 2 is to now draw the chemical symbols and the atoms in the way that they're bonded, with the tip that the first atom listed is typically the central atom. So nitrogen is going to be our central atom. So I'm going to put nitrogen first. And then the other atoms we have to draw are hydrogens, and those are going to surround the nitrogen. So I'm going to put a hydrogen here, here, and there. So there's 3 hydrogens around it. And then part of that second step is to now draw bonds between the central atom and outer atoms. So 1, 2, 3. So I've drawn 3 bonds now. All right. So if you take into account how many electrons I have drawn so far, I've drawn 6 electrons so far because I've made 3 bonds. Each of those bonds, although I didn't draw them, have 2 electrons that make up that covalent bond. So I've used up 6 of my 8 electrons so far. So you got to keep that in mind. So if we look back at the next step, what did we do? We did step 2, place covalent bonds. So if there are extra electrons, add lone pairs to the outer atoms to fulfill their octet. Okay, so we do have extra electrons. We need to use up 2 more electrons. All right, we have 2 electrons left that we need to spend. So it says first to do outer atoms, but to fulfill their octets. So hydrogen here, because it only needs an octet of 2 to be fulfilled. Remember, it's one of our exceptions. Hydrogen only needs 2 electrons for octet. It's because it's a 1s2. It only has an energy level of 1, so it only has an s orbital available. So that to be filled, it needs 2 electrons, and then it has the electron configuration of a helium atom. So that's why hydrogen is an exception. So if you see all these hydrogens here, because these bonds that we formed, hydrogen and nitrogen, are sharing electrons, each of these hydrogens have a fulfilled octet. As written, hydrogen doesn't need any more electrons. Okay, all 3 of them. So if we look at step 3, it says, extra electrons should go on as lone pairs on the outer atoms because hydrogen doesn't need any more electrons. We're not going to place them on hydrogen. Those ones are all, hydrogens are all good there. So we have to move on to the 4th step to place those 2 extra electrons we have. So if there are still extra electrons, then add lone pairs to the central atom. Right? So that is the step that we're going to do. I'm just going to erase this. All right, so we have 2 more electrons to spend, so I'm going to actually place it on the nitrogen, the central atom, as indicated by step 4. All right, and now I have used up all of my electrons. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. This is what NH3 or ammonia looks like. Well, let's check the last step. Now it says check the octet rule of all the atoms. Well, all these hydrogens, like I said, they all have 2 electrons, so those octets are good. I'll just put a little check mark there. Remember, hydrogen only needs 2 electrons, so those are good. Now, if we look at nitrogen, all the electrons around nitrogen, there's 1, 2, 3, 4, 5, 6, 7, 8 electrons around nitrogen, so nitrogen also has a fulfilled octet. So this is what NH3 looks like as its Lewis structure. Let me just clean it up a little bit for you here. So it will look like this, where I put 6 electrons to form the bonds between nitrogen and hydrogen, because there's 3 of them, and then there's a lone pair right there on hydrogen. And we've obeyed the octet rule. We are good. So this is the Lewis structure for NH3. So I think something that a lot of students forget is that in the chemical formula, typically, most times, 9 times out of 10, that first element listed, or first atom listed in the chemical formula, is the central atom, and then you put the hydrogens or the other atoms around that central atom. Okay, so let's do this one now. So silicon and 4 chlorines. So we're going to do the same thing. We're going to count valence electrons here. So silicon, if you look at our periodic table, it's in group 4A. So it has 4 valence electrons. Chlorine, and there's 4 of them. Chlorine is in group 7A. Okay, so there are 7 valence electrons, but then there's 4 chlorines. All right, and so if you add that up, so 28 plus 4 is 32. We have to place 32 valence electrons. So that's step one. Step two is to place the atoms um, in the molecule. So remember, silicon's written first, so this is our central atom. So I'm going to write silicon first in the middle. And then these are going to be, the chlorines are going to be our outer electrons. So I'm just going to place the 4 chlorines around silicon and then form covalent bonds between the outer and central atom. 1, 2, 3, 4. I've drawn 4 bonds so far. So 4 bonds is 8 electrons. So if we started with 32 valence electrons and we used up 8 electrons from forming bonds, because remember, each bond represents 2 electrons, we still have, 24 valence electrons that we still have to use up. All right, so we're not quite done yet. So if we look at the next step, we counted, we placed covalent bonds. So now step 3, if there are extra electrons, and we have 24 extra electrons, start adding lone pairs to outer atoms to fulfill their octet. So let's take a look at one of these chlorines since we're adding to the outer atoms first. So this chlorine, we just look at this one, there are only 2 electrons in its valence shell. Chlorine needs to get to 8 valence electrons to have a complete octet. So I'm going to draw 1, 2, 3, 4, 5, 6 additional electrons around that chlorine. So now around this chlorine, what I have highlighted here, there are 8 electrons around that chlorine atom. So this chlorine has a fulfilled octet. And so now I've used up six of my electrons. I've used up 6 of my electrons. And so I'm going to repeat the same process for the rest of them. So if I draw 1, 2, 3, 4, 5, 6 around this chlorine as well, if I highlight around that chlorine also has 8 valence electrons around it, and then you kind of see the pattern here. I'm going to draw 6 electrons around this chlorine and around this chlorine. All right, and so now you can see all the chlorines have a fulfilled octet, and I've used up the rest of my 24 valence electrons. So I put 1, 2, 3, 4, 5, 6 electrons around additional electrons, or step 3, around 1 chlorine, and I did it 4 times, so 6 times 4 is 24. So now I have used up the rest of my valence electrons. And I mean, you can check your work here. Remember, we had to place 32 electrons down. So if you double check and recount all of the electrons, and remember that 2 electrons reside within that bond, each of those bonds, we have placed 32 electrons. So we used up all those valence electrons that we needed to, and we see that all the chlorine atoms have a fulfilled octet. But remember, step 5 is check octet rule on all atoms. So I'll note that we got to skip step 4 because we used up all of our extra electrons on just the outer atoms. So it's very important that you keep inventory of all the electrons that you place. So we got to skip step 4 because we used up our electrons. So now let's check the octet rule on all the atoms. So chlorine has a fulfilled octet. So let's look at silicon. Remember, each of these bonds has 2 electrons in it. So if we look at the electrons around silicon, you can see that silicon also has 8 electrons around it. It's nice and happy. Every atom here, as drawn, has 8 valence electrons. So this Lewis structure is complete. All right, let's move on to one more example of doing Lewis structures. So here I have a molecule HCN. So I'm going to start this the same way. I'm going to count up valence electrons on all the atoms. So on hydrogen, there's 1 valence electron. On carbon, that's a 4A element, so there are 4 valence electrons. Nitrogen is a 5A element. Nitrogen has 5 valence electrons. So if you count all of those up, we need to place 10 valence electrons total. Okay, that's step 1. Step 2 is place the atoms down. All right. Remember, typically the central atom is written first unless it's hydrogen. So here's one of our exceptions. Hydrogen's written first, so we're actually going to look at the next atom. So in this case, carbon is our central atom. Right? So carbon is our central atom, and then that means hydrogen and nitrogen will be on the outside. Right? Okay, so I think part of step 2 is to place covalent bonds. All right, so a bond between hydrogen and carbon, and a bond between carbon and nitrogen. So I've placed 2 bonds down, so I have used up 4 of my electrons, so I have 6 extra electrons that I have to place. All right, so now we move on to step 3, which is place extra electrons as lone pairs to the outer atoms first to fulfill those octets. So let's start putting electrons on those outer atoms, and we have 6 to place. So remember, hydrogen doesn't need any more electrons, so we're not going to place any additional electrons on hydrogen. So we'll have to actually put them on nitrogen here. So I'm going to place 6 extra electrons on nitrogen. There are already 2 electrons on nitrogen. So it looks like I can put the rest of the 6 electrons around nitrogen, and then that's how I fulfill the octet of nitrogen. So you see here there are 8 electrons on nitrogen. It's nice and happy with 8 valence electrons. Hydrogen also happy because it has 2 electrons. It also has its 2 valence electrons that it needs. So the last step, check octet of all the atoms. So if you look at carbon now, we look at the electrons around carbon. Carbon only has 4. So carbon does not have a fulfilled octet. Well, rats, what are we going to do? So this brings us to one last step. So HCN, this particular molecule, we have to do one extra step in order to get carbon to have a fulfilled octet. So I'm going to add a rule to our rules for the octet rule. So if the octet rule is not met, so in this case for carbon, in our HCN example here, carbon only has 4 valence electrons, yeah? So you want to make multiple bonds with the central atom. And how we do that is essentially move lone pairs from adjacent atoms to form a multiple bond. Multiple bonds. And so I think I'll show this example later, but essentially what we're going to do is instead of putting the lone pair on nitrogen, we're going to turn this lone pair into a double bond or into another bond connecting carbon and nitrogen. So let me actually first, before I get into that, talk about what a multiple bond is. So when we talk about up until now, we've only talked about single bonds, single covalent bonds, where 2 electrons form one bond. So in multiple bonds, those just involve sharing more than a pair or 2 electrons. So, you remember we have a single bond, essentially 2 atoms will share 2 electrons. We typically draw the dot structure like this. You have 2 atoms, it shares 2 electrons. We can draw the Lewis structure, Lewis structure as a line to form those bonds. That bond, those 2 electrons becomes one line. So if we start to share more than 1 pair of electrons, that's when we form a double bond. So in a double bond, we have 2 atoms that share a total of 4 electrons. So as a Lewis dot structure, you can think, okay, we have 2 atoms here, and they're going to share a total of 4 electrons. So how you would draw that Lewis structure or that bonding arrangement is literally you draw 2 bonds between those 2 atoms. All right, so each of these lines denotes a single bond. So together, 2 lines is a double bond, where each of these lines represents 2 electrons. But in a double bond, there are 2 bonds, so that's a total of 4 electrons. So you can predict what a triple bond is. A triple bond is where two atoms will share a total of 6 electrons. All right, and so if we have two atoms, so X and X, they're going to share a total of 6 electrons. So 1, 2, 3, 4, 5, 6. So if we wanted to draw that as a Lewis structure, line structure, we would draw 3 lines to connect those two atoms. And you can predict what a quadruple bond would be. A quadruple bond would be when two atoms share 8 electrons total, and then you would have 4 lines connecting two atoms to make four bonds. Right? And so here's just like another depiction of multiple bonds. So diatomic nitrogen, the nitrogen that makes up the majority of our air. Nitrogen, diatomic nitrogen, those two nitrogen atoms actually share 3 pairs of electrons, or 6 electrons total. That's what we have here. So there's 6 electrons total between these two nitrogens. And so 6 electrons will form a triple bond that connect those two nitrogen atoms to form our nitrogen molecule that we have in our air. So let's go back to our HCN example, right? So let me just redo this. So HCN, valence electrons, I think there was a total of 10. We had 10 valence electrons. So we drew the molecule like this at first, right, where we placed electrons on the outer atoms first to fulfill nitrogen's octet. But we said once we got to this step, we saw that carbon has a deficient octet. That carbon only has 4 electrons around it. We need 8. So if we remember, every bond is 2 electrons. So we need to form 2 additional bonds to carbon in order to fulfill its octet. So what I'm going to do, the only atom that has extra lone pairs around it is this nitrogen. So I'm going to move one of the lone pairs to form a multiple bond with carbon. I'm just going to do this one step at a time so you can see it. So if I move one lone pair to carbon, I'm going to form a double bond, leaving, there's still 2 lone pairs on that nitrogen. Okay, they didn't go anywhere. It was only this pair that moved. Right? So now if we check our octet rule, nitrogen still has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it, so its octet's still good. Carbon only has 1, 2, 3, 4, 5, 6. So you see here there's only 6 electrons around carbon, so we still need another lone pair, or we still need another bond to carbon to fulfill its octet. So I'm going to move another lone pair to form a multiple bond with carbon, our central atom. So it will look like this. So I did it in multiple steps. So now you see carbon around it has, and remember each of these bonds has 2 electrons on it. I'll just put that there to remind you. If we look at carbon now there are 8 electrons around carbon, our central atom. Whoops. So carbon has a fulfilled octet now. We can still check our work with nitrogen. So nitrogen, the electrons around nitrogen, there are 1, 2, 3, 4, 5, 6, 7, 8 around nitrogen. So nitrogen has a fulfilled octet, and we can do the same thing for hydrogen. Well, we didn't really do anything to hydrogen, but it still has 2 electrons. That's all it needs. So everything's good. Everything has a fulfilled octet, nice and happy. So let me just redraw this without drawing all those electrons there. So this would be the Lewis structure for HCN. So when the central atom is deficient in its octet, you need to form multiple bonds. So that's this last step here where it says, check your octet rule. If that central atom is not met, you need to start making multiple bonds with the central atom. And in order to do that, you need to move lone pairs, maybe more than 1 or 2, from the adjacent atom to form multiple bonds with the central atom. So you're really just going to have to practice these. All right. So remember, when we're moving lone pairs, we're not changing the number of electrons. We're just moving where those electrons reside at. So are they as a lone pair on one atom, or that we can move that electron, those two electrons, to form a bond between two atoms instead. And that's how we fulfill the octet for the central atom when there's not enough. Okay, so here's another example involving multiple bonds. So carbon and oxygen. I don't have to tell you that there's multiple bonds, but we're going to go through our steps the same way. So the first step is to count valence electrons. So we can do that. Carbon and oxygen. Carbon is group 4A, so 4 electrons. Oxygen is 6A, so total of 10 valence electrons that we need to place. So there's only 2 atoms here, so we don't really have to worry about central atoms and stuff. We can just place them because it doesn't matter if it's carbon first or oxygen first. All right, so since there's only 2 atoms, so I'm going to put a bond between them. So I've used up 2 of my electrons. But I need to get to 10. So now I need to start placing electrons on the outer atoms. Well, both of these are technically outer atoms. We don't have a central atom. So I'm just going to start placing those electrons. So I have two electrons in the bond. So 3, 4, 5, 6, 7, 8. And then I need 2 more, 9, 10. So note how I stopped here because I see that carbon has a fulfilled octet. All right. So now let's check our octet rule. Okay, so I've placed our 10 electrons that we need. So let's check the octet rule. So if I look at carbon, there are 1, 2, 3, 4, 5, 6, 7, 8. So carbon is good, but oxygen only has 1, 2, 3, 4 electrons. So it needs 8. So we need to give that oxygen an additional 4 electrons to fulfill its octet. So there's only one place where we can do that. So remember our rule, this oxygen is deficient, so we need to start making multiple bonds to it. There's only one place to form those multiple bonds, and it's this adjacent carbon. We're going to move these lone pairs to start forming bonds, multiple bonds with that oxygen. So oxygen, as written right now, has 4 valence electrons, so I need to get to 8. So that's an additional 4 electrons, so I know that that's an additional 2 bonds. So I'm going to move 2 of those lone pairs on carbon to form multiple bonds with oxygen. So then our new Lewis structure, so there's our original bond. So I'm going to make an additional multiple bond and another multiple bond there. That leaves 1 lone pair on carbon. And then, we still have this lone pair on oxygen, so I'm going to keep that there too. All right, and so you can double check your work, make sure that there's 10 valence electrons that we had to place. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we placed 10 electrons. All right, now let's again check our octet rule. So if we look at our octet rule, carbon, so there's 1, 2. Each of these bonds has 2 electrons. So this is a triple bond, so there's a total of 6 electrons here. So there's 6 electrons there, plus 2 on carbon. That's 8 on carbon. So carbon is good for the octet rule. And then look at oxygen as well. 6 electrons come shared from the triple bond, and then 2 additional electrons on oxygen as that lone pair. So oxygen also has 8 valence electrons that it needs. So I've given you a couple of examples of how to come up with Lewis structures with neutral molecules, neutral covalent molecules. So there's one other type of Lewis structure that we can make, and that's Lewis structures of polyatomic ions. So remember, these are those lists of polyatomic ions that are made in ionic compounds. So in all of those neutral examples, Those, like, four examples that I showed with Lewis structures, those were all neutral molecules that were covalent. So you can also draw Lewis structures of polyatomic ions. So a polyatomic ion has both an ionic component because it's charged and a covalent component. So if we look at these examples of different polyatomic ionic compounds, we can identify the polyatomic ion. So in this case, in NH4Br, so NH4 is a one of our polyatomic cations, but we can also see that it's made up of entirely non-metal elements. So that makes it a covalent molecule because it's comprised of all nonmetals. And so since it's all nonmetals, we can make a Lewis structure like we did with all of our other, non-metal only covalent compounds. So NH4 in this ionic compound is made up of nonmetals, so it is covalent. It has covalent properties, but it's also charged like in ionic compounds. So this is where polyatomic ions kind of have this dual personality to it. All right, and then if we look at the second example, sodium sulfate, we can also identify a polyatomic ion. That is sulfate here. So sulfate, if you look at the our naming chart, our naming handout, SO3 is sulfate with a 2- charge. So also in sulfate, sulfur and oxygen, those are both nonmetals. So it is entirely covalent, but it's also charged, that we have to take into account. So what I am trying to get at here is that these polyatomic ions have a covalent component to it, so we can draw a Lewis structure. But they are also charged, so we need to take into account these charges that are denoted there. And it's quite straightforward. So we're actually going to follow the same rules for drawing Lewis structures. We just have to adjust the number of valence electrons in step 1 to account for this charge. So for example, in that first step, when we want to draw the Lewis structure for one of these polyatomic ions, so in that first step, when you're counting valence electrons, for a polyatomic ion, adjust the final electron count by the charge. So, for example, NH4 ammonium is a +1 charge, so we want to remove one of those valence electrons from that total count from step 1. Or sulfate, in this example, it has a -2 charge, so after counting the valence electrons from sulfur and oxygens, you're going to add an additional 2 electrons. Then you're going to go through the steps, the same exact steps. So let's actually draw the Lewis structures for these. So let's do NH4 plus first. So it's the same steps. Let's do valence electrons first. So that's step 1. So nitrogen has 5 valence electrons. 4 hydrogens have a total of 4 electrons, so that's 9. But then we need to account for the charge. So since it's a +1 charge, we need to remove one of the electrons. So remove one of the electrons to account for charge. So there's a total of 8 valence electrons that we need to place. So this is the only new step. We're going to go through the rest of the steps for drawing Lewis structures exactly the same. So that was step 1, valence electrons. Step 2, place atoms in bonds. So nitrogen's written first, so it's our central atom. So nitrogen, and then there's 4 hydrogens, so I'm going to just draw 4 hydrogens with bonds to it. So you see I've drawn 4 bonds. 4 bonds will require 8 electrons, so I'm done. There are no extra electrons to put on the outside or on the central atom. 4 valence electrons, 4 bonds, this is done. The only last thing that you have to do is check octet rule. So hydrogens have fulfilled octets because there's 2 electrons in each of those bonds. This nitrogen, there are 2 electrons in each of those bonds. So there are 8 electrons around nitrogen, so Nitrogen's good as well. And then actually the real last step for polyatomic ions is to denote the charge on the molecule. So typically what you do is put the whole thing in brackets, the whole Lewis structure in brackets, and put the charge. So that's the last step for a polyatomic ion, to denote the charge on the structure itself. All right, so let's do sulfate, SO3 2-. So again, same steps. We need to count valence electrons. So sulfur has 6. Oxygen also has 6 valence electrons, but times 3. So what is that, 24 valence electrons? But again, we need to take into account charge. There's an extra 2 negative charge on sulfate, so we're going to add 2 additional electrons for the charge. So we need to place a total of 26 valence electrons. All right, that's our goal number to get to. So that's step 1. Step 2, place atoms. So sulfur here is our central atom. So sulfur in the middle, and then we're going to put 3 oxygens around. All right, so I've drawn 6 electrons so far. So I need to get to 26. So I have a lot of electrons to put down. So I'm going to start filling up the octets around the oxygens on the outermost atoms. So, okay, so 6 electrons. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. All right, so I have 24. So there's 24 electrons I've placed down. So I still have 2 extra electrons. So remember that I only placed 6 extra electrons on each of these oxygens because doing so would fulfill the octet for each of them. So I need to place 2 more electrons. All of the outer elements atoms have fulfilled octets, so now it will go on the central atom. So those last 2 electrons will go on sulfur itself, the central atom. Now let's check octets. So oxygen here has 1, 2, 3, 4, 5, 6, 7, 8. So oxygen is good, and it's the same thing for the rest of them. And then if we look at sulfur, so sulfur has 3 bonds to it. So 1, 2, 3, 4, 5, 6, 7, 8. So sulfur also has 8. They're all good. So all the octets are complete. And then the last step for polyatomic ions is to put brackets around the whole thing and indicate the charge. So sulfate is a 2-, so I'm going to put 2- right there. So I'll post a handout a little later to help you practice doing the steps for making Lewis structures for different compounds.